Okay, so we said that to find dj dw2, it's going to be exactly the same as the 111 network because from here to here is the same. So if we look at dj dw2, we're going to have to go through the same set of functions, and so the chain rule will give us the same result. So we still have this, the same result, which we can write in the same way here. And here we have that delta 3 is the entire set up to here, which if you write it out, if you calculate these, you get this, minus the quantity y minus y hat, and then the derivative of the activation function, or the derivative in our case of the sigmoid function, evaluated at u. So this is the same result that we had before. So now we want to move on to the calculation here. So we have two weights here, so this is possibly going to give us different results than before, but we still want to calculate the derivative of j with respect to w11, w11, in order to figure out how much we should update w11 by. And then we also will want to calculate the derivative of j with respect to w, which I say this is 1, 2, in order to figure out how much we should update w12 by. And actually, if you think about it, if you take the derivative of j with respect to this, you're going to go through actually the same path that we did actually in the 1, 1, but then we're going to have another exact same path, but with respect to w12. So actually the form is going to be the same, but let's just check that. And let's remember that this z2 is now going to be x1 w1. Maybe I won't be saying this the right way. I guess I should say w11, x2 w12, and we're going to add those up to get z2. So we have that here. Z2 is this calculation, and we want partial of j with respect to w11, partial of j with respect to w12, and we can also imagine that we can define what we call delta 1 before. Now we're going to need maybe a delta 1, 1, and now we're going to need a delta 1, 2, maybe. Once we get these calculations, or once we do these, we can store the two of them in a matrix if we want to. And we will do that, but first we want to get them individually and then place the results in a matrix. So actually the only difference in the calculations that we want to do now in the first layer, and the first layer of the calculations in 1, 1, is that we need to add a subscript to the previously used W1 notation. So here we have the partial of j with respect to, before we just had this, now we have to put that 1 there, and this 2 here. And then if we do all the calculations, they're all going to be the same, except the last one is WZ2 with respect to W11. We didn't have 1, 1, we just had 1 here. And then with respect to, for this one, it's going to be with respect to W12. So we can see that actually this and this are going to be the same. So the delta, we might have thought we're going to need a delta 1, 1 and a delta 1, 2, but actually we can see that here we have a delta 1, 1, and here we have a delta 1, 2, but they're actually the same. So the only difference here is this and this, and our delta, I shouldn't have said delta 1, 1, I should have called it delta 2, 1, and delta 2, 2. Anyway, and these are actually going to turn out to be equal. And in fact, they're both equal, and they're both actually equal to the delta 2 that we used in the 111 network. These are the same, so they're both going to be equal to each other and equal to the version of delta 2 in the 111 architecture. And then we need the final term here and the final term here, and they're not going to be exactly the same as before, but you can see, well, if we want the derivative of z2 with respect to w11, if we look at this calculation, this is z2. If we want the derivative with respect to w11, it's going to be x1. This is going to be 0, and this is going to be x1. So, and then if we want the derivative with respect to w12, then there's no w12 here, so this is going to be 0, and all we're going to be left with is x2. So the two derivatives are going to be the answers to the two partials at the end are going to be x1 and x2. So these are going to be x1 and x2. So then if we're using the delta notation, we can say it's this times this, but we can say this is x1. So it's delta 2, 1, x1, and this one is going to be delta 2, x2. Now, as I said before, or at least it's said in the text, that sometimes we call these the activities. So if we call these the activities x1 and x2, so in the book we said that we might call the activity of this node x1, the activity of this node x2, the activity of this node a2, the activity of this node y hat or a3. So we sometimes use that word for the output of the node. Sometimes it's called the activity. So this says that the derivative is proportional to the activity of node 1, and this says that this one is proportional to the activity of node of the x2 node. So now we've done the work that we wanted to do. We have the derivative with respect to w11 and w12, and we also did the calculation earlier for the derivative with respect to w2. And by the way, this really shouldn't, maybe this is a capital and it shouldn't be a capital here, since this is a single w, but sometimes we'll call it a capital W, and we'll say that the matrix consists of just one element. So I guess we could say that we could allow it to be a capital. But on the other hand, this, well, yeah, that's right. Okay, now if we want to put the two results, these two results here, into a matrix, we could do that. So we could just say we could just put this result as the first element of the matrix and this result as the second element of the matrix. So we can put those here, and we can call that the derivative of J with respect to the weight matrix. Now, this is capital W1, so that really refers to these two weights together as a matrix. But this sounds very strange to say the derivative of J with respect to a matrix. That sort of doesn't make any sense. But here what we mean by it is it's just the derivative with respect to the first weight, and then the derivative with respect to the second weight, and we just put those into a matrix, and we can call it this. And then we can also put the two deltas that we just defined, delta 2,1 and delta 2,2, which happen to be the same thing, but we can still put those in a matrix as well. Okay, now, and then of course we could also, and we have done before, we can also put the x's, there's two x's here, we can put those in a matrix as well and call that a capital X. So we have that here. And now we just want to express these two equations here and here, but maybe we want to do it in matrix form. And we already said that we can put these together into a matrix, and we'll give it the name, derivative of J with respect to the matrix W. Now again, I say that sounds very strange, but we're just using it to denote this matrix, which has these two elements in it. Okay, anyway, so if we want to express these two equations, they have a very similar form. We can say this one is this times that, and this one is this times that. They're very similar. And if we put these two into a matrix, and we put these two into a matrix. Now, typically, we are going to put x1 and x2, and we're usually going to call it a row matrix. But here, we put this into a column matrix, and we put the delta 1, delta 2s into a column matrix. So they look like this one, and this is column, and this is column. So we want to write some kind of equation. This is our derivative matrix, which is just means this. We just said that. And then we want to write it's equal to, and we want a matrix equation here. So we see that the answer should basically be, we're going to need a delta times an x1, and we're going to need a delta times an x2. But we've defined this matrix, this delta matrix, and we have this x1 defined, but this doesn't really work. Like for example, first of all, what's the size of this? This is a 2 by 1, 2 by 1. So this one here is a 2 by 1, and this one here is a 1 by 2. So if we multiply those, that doesn't give us what we want, because that gives us a 2 by 2, and this is not a 2 by 2, so that doesn't work. Now I wrote the transpose here, and if I had the transpose, then this would be a 2 by 2, a 2 by 1. So would that work? Suppose I had a 2 by 1 here, 2 by 1. That we can't even multiply those two. So it doesn't seem to work. How are we going to write some kind of equation where we have this times that? And really what we really want when we multiply this out is just we want to end up with something like this, that is a vertical matrix. We want the formula for this one and the formula for this one. And the formula for this one is delta 2, 1 times x1. So we want the formula to be, we want the result to be delta 2, 1 times x1, and then delta 2, 2 times x2. So that's what we want to end up with, and then we'll say that this is equal to that. But this doesn't work, and the transpose doesn't work, and okay, so we're stuck. So, however, we can talk about something called element by element multiplication. Now let me rewrite this, because I do want the transpose, but let me just put it in there, what it would look like, just so you can visualize this. So instead of having this, I'll write the transpose like it is, like this, so that we can sort of see it easily. So what I really want to have is I want to get a 2 by 1 matrix, just like this, and I want the first element to be delta 1 x1, and the second element to be delta 2 x2. So that's what I really want. But I don't, if I can't even multiply these, this doesn't work. Matrix multiplication doesn't work, because we just said this is a 2 by 1 and this is a 2 by 1. We can't even multiply them. So we do have something. What we really want is element by element multiplication here. So I want some operation where the result will be a 2 by 1 matrix, and the first element in that 2 by 1 matrix will be delta 2, 1 x1, and the second one will be delta 2, 2 x2. But this doesn't work. Regular matrix multiplication won't do that. So we do have something called element by element multiplication, and we could just call it element by element multiplication. There's also another name for it. I don't know the history of this. I think it has to do with some application in physics or whatever. But anyway, it's just element by element multiplication, and it is sometimes called the Hadamard multiplication of two matrices, where it just means element by element multiplication. And we're just going to make up a symbol for that here. So we'll use this to mean element by element multiplication. We need some symbol, and it's not just regular matrix multiplication, and we don't have any other symbol for it, so we're just going to make up a symbol. And it means element by element multiplication, or Hadamard multiplication. And so with that, now we can, if we put that in there like this, then this means multiply this times this and multiply this times this and just make a 2 by 1 matrix that has those two elements in it, which is really what we want. So if I do that, if I do this element by element multiplication, this is what I get. This times that here, this times that here. And that's really what I want, because now I'm saying, just like I wanted to say, that the partial of j with respect to w11 is this times x1, and the partial of j with respect to w12 is this, whoops, that's wrong, times x2. So with this creative use of a new operation, we can now express the kind of a matrix equation with this special multiplication. So it's this times this, but remember this was, our original x was written horizontally. So really if we want to write it as x, so we want to replace this by x as this. Let's see, can I put this in here? X, sorry, capital X equals that. No, that doesn't work, does it? Okay, so capital X equals that. No, wrong. Without the t. So, sorry, we don't want that t in there. So this is capital X. So if I want to write it this way, I have to, and I want to use the symbol x here, I should say x with a t at the top, so the transpose of x, because this is x. If I want to write it vertically, I have to write x with the transpose. So with all of, and then we call this matrix like this. We give it this name. So this matrix is this, and then this is x transpose, which is here. I just reversed the order, but that doesn't matter. That just means I put x1 over here and x2 over here. So now we can express this in this notation. This is not matrix multiplication, right? This is just element by element, very simple multiplication. So now we have this expression for dj with respect to the so-called matrix W1, which we said doesn't really make a lot of sense, but it just means this matrix. So we have that matrix, and we have a way of expressing its calculation here, which is just a summary of this stuff here. And we also have the original one with respect to the, we have the original one, where's that? That is the dj with respect to W2. In other words, this weight here. We have that one already. That we did already. Actually, we did that in the 111 architecture. But anyway, we have it here. So now we have expressions for dj with respect to W1, W2, and also with respect to both of these. That's what we just finished. So we have everything we need. And so we can write, how are we going to update W2? And this is the same way that we did it before. Oh, sorry. Okay, this is pretty bad error here in the text. So this actually should be 1, and this should be 2, because 1 is the one with the matrix, and 2 is the one without the matrix. So this was the new W2. That's the one closer to the right-hand side, closer to J. And that's not a matrix equation. But this one is a matrix equation. It's a matrix equation. And this is W1, how to update W1. And we use this, we subtract this, or r times this, which is this is, remember, a matrix. We've just been talking about that. So we just take the original weights, there are 2 of them, and we subtract the appropriate dj, dw's from them, with the multiple of r in there as well. Now let's just go back and compare what we got here with the 111 network for dj, dw1. And this was what we got. Now, if we think about what we just showed for the when we were doing the 2, 1, 1 matrix, that is where we have 2 nodes at the beginning, it looked very similar to this. Let me fix that here and go down and show you that they look quite similar. So this was for the 1, 1, 1 matrix, and this is for the 2, 1, 1 matrix, and they look very similar. We put the X over here. It doesn't make any difference in this case. But otherwise they look quite similar. They both have delta 2 in them. And then this one has just X, because there was only one X, whereas this has the matrix X and the transpose. Now, if we think of the transpose of a single element as just the element itself, which seems reasonable, right? If you take the transpose of just a single element, you'd say, well, you don't get anything different. Or even if you consider this as a 1-by-1 matrix here, and you take its transpose, you get the same thing back. So if we think of the transpose in that sense, then the transpose of this is just this. So then we really get exactly the same form here. Of course, this is a matrix, this isn't, but we get the same thing. So, but this is kind of more general because it does have the transpose there, and it works. So we could say that this equation works for the 2, 1, 1 matrix, the 2, 1, 1 network. But it also we could say it works for the 1, 1, 1, as long as we think of this, the transpose of a single element, as the element itself. So this is kind of more general than this expression. So we say that here. In some sense, we may want to say that equation 1130, the new one, above, is more general than the 1, 1, 1 architecture equation. And then, as we said, we can write our update equations like this. And then we are done with what we need to do for the 2, 1, 1 network. We know how to update this weight. We know how to update these weights. So the next thing we want to do is try and write some of the code here. So first we write the code for the 1, 1, 1 network. And that means we have to write what's called the forward propagation and the back propagation. So that means we have to express what happens to X. So X gets multiplied by W, and then that gets, we put that into a sigmoid function, and then we multiply that times W. We want to do this in our code, and then we get this, and then we put that into a sigmoid function, and then we can also define the cost function here. By the way, I've been using the word error and cost sort of interchangeably, but really the error refers to a single, when you run a single X through, you get the error, you get some error, which is just this minus this, but we define the cost to be this, and we have the sigma there to indicate that we're talking about the cost over many values of X, or many examples. Anyway, so we have to, we write some R code to do this, which is very simple R code. And then we have to write the R code to change the W's. And we know the formulas for those, so it's probably not going to be all that hard to write that either. So what we'll do is we'll pass one example through the network here. Then we'll take the derivative and we'll use that, and we'll then we'll write an equation to change this, and we'll write an equation to change this, and we'll have new weights, and then we can test the network again with another example, and we could just repeat this over and over again with each new example, and each new example would cause us to change the weights, and that's the whole process. So then we'll write the code for that, and then we'll write the code for this network as a separate set of code. And here we want to feed in 2 inputs and figure out these things, and then go back and write some code to adjust this and to adjust this, and we will have completed that code. And then, of course, we're going to do a similar thing for the 2, 3, 1 network. But you can see it's going to be, you can sort of see where it's going to go. It's going to be very similar to what we do here. But first, let's get the code for these first 2 network architectures.